This is a session on the analysis of the most basic of power systems, which is one of the topics of this course. This is the power system formed by a source, an AC source that could be the secondary of a power transformer or perhaps the simplified version of a generator, feeding a load that in this discussion I will call factory, because the F is easier to identify as a subscript than L for load. Joining the source to the load, there is a cable, a feeder, represented by its resistance and the reactance associated with the inductance of that cable. The source voltage is given as Vs. Of course, it's a phasor with RMS value and a phase associated with it. And at the factory we have Vf, the voltage at the factory, voltage at the load. As soon as we apply that voltage, there is a current I, another phasor flowing through the circuit. But that current will produce in R here a voltage drop, VR, and in the reactive part of the cable a voltage drop, Vx. We know that VR is R times I. That means that the voltage drop VR is parallel to the phasor I, is in phase with I, of course. And Vx, the voltage drop in the reactive part of the cable, is computed as Gxi. J is 90 degrees. That means that this voltage drop is perpendicular to the phasor of the current. But we knew that this voltage is perpendicular as a phasor to the phasor representing this current, and this voltage phasor is parallel to the phasor of the current. If we choose, as we usually do in the phasor problem, we choose one of the many phasors as our reference for phase, as the 0 degrees value, and that is arbitrary. If we are not given any phasor with 0 degrees, we choose one. Well, in this case, I will choose this voltage, the voltage at the load, the voltage at the factory, as my phase reference, 0 degrees. And the current through that factory is like so in this phasor diagram. What this tells us is that the current in the load in the factory is lagging by this angle. This source, this factory, is slightly inductive. This angle, theta f, theta at the factory, is the angle of the power factor of the load. The cosine of that angle is the power factor of this load. This is an inductive load the way it is drawn. The current is lagging behind the voltage at the same point at the factory in this case. Well, let's see again. We were saying that load is inductive. Well, if the load were absorbing the same amount of current but with a smaller power factor, the power factor angle would be bigger. Here we have a more inductive load, a purely inductive load, a resistive load. In that case, the factory is represented by a resistor. In this case, the factory is slightly capacitive. Purely capacitive. The factory is represented by a capacitor. And in this case, the factory actually is delivering active power. It's a generator. Well, let's make a small parenthesis here to analyze the flow of active and reactive power in one simplified power system like that. If the load is semi-inductive, is slightly inductive, not pure inductive, like here, if that is the case, this is the angle theta of the power factor of the load. We say theta is the phase of the voltage, phase of Vf, 0 degrees in our case, minus the phase of the current. It's always that. In this case, phase of Vf minus phase of I is this angle, and it's a positive number in this case. But if theta is positive, the cosine of theta is greater than 0, and the sine is greater than 0. That means that P is going to be greater than 0, and Q is greater than 0. These formulas give us the absorbed active power and the absorbed reactive power in an element. Well, that means that if this is the relationship in phase between voltage and current in the factory, that factory is absorbing positive power, active power P, and it's also absorbing positive reactive power. If the load is more inductive, the relationship remains the same. The load is absorbing positive active power. The load is absorbing positive reactive power. If the load is purely inductive, like here, the power factor angle will be voltage phase minus current phase, which is 90 degrees in this case. The cosine of 90 degrees is 0, so the active power of the factory will be 0 watts. And the reactive power will be dominated by the sine of 90 degrees, 1, so Q will be just VI, positive, the apparent power. In short, an inductor absorbs no power, no active power at all. An inductor absorbs only reactive power, and the value is VI, the value of the apparent power in that inductor. In this case, the factor is represented by an inductor. Now, if the load is resistive, like so, the power factor angle will be 0. The absorbed power, active and reactive, is dominated by the power factor cosine of theta. Cosine of 0 is 1, sine of 0 is 1. So a resistive load absorbs only active power equals in value to the apparent power and the load VI. And I repeat, if the load is resistive, the load absorbs no reactive power at all. If the load is semi-capacitive, in this case, phase of the voltage at the factory minus phase of the current is a negative number, which means that P will be positive and Q will be negative. A capacitive load absorbs positive P and absorbs negative Q, which is a way of saying that a capacitive factory absorbs active power and produces reactive power. If the load is purely capacitive, again the power factor angle of the factory will be phase of the voltage, we've chosen that to be 0 degrees, minus phase of the current, which is 90 degrees in this case, is 0 minus 90 degrees. Let's compute the absorbed power, both the active and the reactive, at the factory and the load. First, the cosine of minus 90 degrees is 0. So the active power is 0 in a purely capacitive load. A capacitor absorbs no active power. Sine of minus 90 is minus 1. So Q is negative. Yeah, it's negative. In short, a capacitor absorbs no active power and absorbs negative reactive power. So that is a capacitor produces reactive power VI equal to its apparent power. In this case, the power factor angle is greater than 90 degrees. If that is so, the cosine turns out to be negative. So the absorbed active power P will be negative. In short, this factory will be absorbing negative P, which is a way of saying it is producing P. It is producing active power. It is a generator. And that's the end of that parenthesis about the flow of active and reactive power in a load, depending on its power factor. Let's go back to our circuit. Well, in our circuit, we have said, let's refresh ideas, that the voltage drop in the resistive part of the cable VR is going to be in phase with the current phasor, with this current phasor. So VR will be drawn parallel to this phasor, like so. The voltage drop VR in the resistive part of the cable is parallel to the phasor I. That's right. And Vx, the voltage drop in the reactive part of the cable, is going to be perpendicular to the current phasor, perpendicular to this one, like so, like so. Those are the voltages Vf, Vr, and Vx. If we add together Vr with Vx like so, that voltage is what? This one plus this one. What voltage is that? Yes, I made a pause for you to answer. What is the voltage of Vr plus Vx? It is the voltage from this point to this point. It is the voltage on the cable. That is correct. But now if you add the voltage at the factory with the voltage at the cable like so, what do you get? Another pause I make. Vf plus Vr plus Vx. What is this voltage phasor? Absolutely correct. That is a voltage at the source Vs. Let's identify some of the angles in here. This angle theta f is the power factor angle of the load of the factory, right? Is the angle between Vf and I at the factory, the power factor angle at the load. But this angle here is the angle between this voltage Vs and this current, this one, this voltage Vs and the current. That angle has to be the power factor at the source. Absolutely. The difference between those two, delta, is the phase difference between the voltage of the source, this voltage, and the voltage of the factory. Delta is the phase difference, I repeat, between Vs and Vf. The importance of that angle will be clear when we see synchronous generators in this course. That angle will be identified with the torque that we need to apply to the generator that is feeding the load. We call that the torque angle, but that is for the future. For now, it's sufficient to say that if we subtract the power factor angle of the source minus that of the factory, we get delta. So that means that this equation is backwards. This subscript should be here and this should be there. All right. If we leave the current the same and the voltage at the factory the same, and we change the power factor, this angle, power factor angle of the load, we make it bigger, so the whole figure becomes like so. If we choose to have a purely inductive load like so, then the situation changes like so. All right, so you see, for different values of the power factor of the load, the diagram rotates correspondingly. Do you agree with me that of all of the possible power factors, this is the one in which Vs from here to there and Vf, the value of the voltage and the load, differ by the most volts? In any other case, the difference in magnitude in RMS volts between Vs and Vf is not as dramatic. This is the one in which the difference between the voltage at the source and the voltage at the factory in RMS volts is at its peak, at its maximum, and it's equal to this value here. What is the power factor angle for this situation? This angle. Let's see. Let's see for a moment. Let's see. What is this situation? This angle is the power factor angle at the factory. But let's observe that in this little triangle, which I'm going to draw here separately, that little triangle is a right triangle with this size VR. In magnitude is Ri, only the magnitude, and this side is Vx, which in magnitude is just Xi. Do you agree that this angle can be identified as the angle whose tangent is Xi over Ri? In short, that little triangle has an angle there that depends only on the values of this R and this X of the cable, or maybe not even in that, but in the ratio between them. That is very interesting. That is interesting. What this says is, if we have a factor, if we have a load whose power factor angle has the same value as the characteristic angle of the cable, arctangent of X over R, in that situation we're going to have the greatest difference between the magnitude of the voltage at the factory and the voltage at the source. Maximum voltage drop. That's right. In this case, the difference is not as dramatic. Again, let me call this the power factor angle at the factory. This is the characteristic angle of the cable given as the arctangent of X over R for the cable. This is the power factor angle at the source. This is the power angle. And what else? Observe this, please. This angle is this one, the power factor angle here at the factory. So this is the difference between this one and this one. And if we subtract 180 degrees minus this one, we obtain the angle in here. Excellent. So there is a relationship of angles between the different phasors in that diagram. Please do not forget that the angle here of this triangle does not depend on the load at all. That depends only on the ratio between X and R of the cable. In this case, the factory is resistive. Capacitive. And in this peculiar case, for this capacitive load, we observe that the little triangle has rotated so that in magnitude Vs is equal to Vf. In short, this triangle has two sides that are equal. We call that an isosceles triangle, and it's a particular case that occurs sometimes in analysis of power systems. And in cases where the load is completely capacitive, like here, this is the power factor angle. In this case, we have the very peculiar and strange situation in which the voltage at the factory is way bigger in RMS volts than the voltage at the source. That's right, we apply so many volts here and we get way more volts at the factory. That can be counterproductive. We may apply 120 volts here and get 300 volts at the factory and burn whatever is connected to the factory there and get in trouble with the customer. Now, consider a case where we do not change the power factor of the load. No, this angle is constant. And we don't change the magnitude of the voltage of the load. There's also constant. We only change the value of the current. Only that. Well, we make it bigger. This angle is still the same. This angle is still the same. That's right. Our tangent of x over r is still the same. Right? Just for the sake of reviewing that, let's write the names of those angles. This is the power factor angle at the load, the power factor angle at the source, this is the torque angle, and this is the cable angle. Our tangent of x over r. If we extend this line, we know that this angle is this one. And we can do whatever analysis we need for our system. Now, a few questions. Think of this question. What would happen graphically? This is a question that may come back to visit you in one exam. What happens if we maintain the value of the voltage at the source as constant, and we maintain as constant also the power factor of the load, theta f? So this is also constant, the power factor of the load. And the only thing that we change again is the value of the RMS amps. Alright, here is another exercise. The voltmeter readings at the factory and at the source are the same, 125 volts. These are part of your exercise assignment for this week. The ammeter reading at the factory is 63 amps. The feeder is known to have a resistance of 60 milliohms and the reactance is 5.5 times the value of the resistance. The questions are, what are the active and reactive power at the factory? What are the active and reactive power at the source? Now another exercise also for your assignment of this week. A voltmeter at the source reads 140 volts, that is Vs. The voltmeter at the factory reads 115 volts, that is VF. The feeder manufacturer says that the reactance in that cable is 5 times the resistance of the cable. An ammeter at the factory reads 33 amps. A wattmeter at the source reads 3 kilowatts. What are the active and reactive power at the factory? What percentage of the active power delivered by the source is lost in the feeder as heat? And last, also for your assignment of this week, consider a load of 4 kilovolt ampere with a power factor of 0.0707 inductive. The feeder has a resistance of 60 milliohms and the reactance is 6 times the resistance. If the voltage of the source is 140 volts, what is the voltage of the load? And the last exercise also for your assignment is a 140 volt source delivers 4 kVA through a cable whose values R and X are given as so. And it's delivering to a load that is connected through that cable. The question is, what is the voltage on the load? In this case, what I'm asking is, what are the RMS volts at the load? What are P and Q and the load, the active and reactive power absorbed